Last ZKProof, we almost had you as a speaker in our conference, but it didn't work out. And this year you managed to arrive to us and tell us about some security vulnerabilities that you found, where I'm very eager to hear. This is a presentation, an invited talk. Thank you very much.
Thank you, Jonathan. Welcome back, everyone. So today I would like to introduce to you a new type of attack on an incorrect implementation of the Fiat-Shamir transform. This was discovered as part of an audit that was performed together with my colleagues, Maxim and Vesco from OpenZeppelin. Before we delve into the details of the attack, I would actually like to give a bit of historical context. As I said, the attack was discovered as part of an audit. In fact, it was part of a Linnea Plonk verifier audit. Initially, we had some theoretical concerns regarding the underlying Fiat-Shamir transform implementation. It turned out that our concerns were actually valid in the sense that they were exploitable in practice, making the finding a critical vulnerability. We have promptly communicated that to the client, and this was swiftly fixed. Later on, however, we have realized that there is an extension. In fact, the attack can be generalized, and in fact, it may affect snark-based snark implementations which use KZG as polynomial commitment schemes. Before we see the full details, I would like us to pause and think about the following problem. Can you solve this system? This is a linear system of two equations with two unknowns, where W1 and W2 are the unknowns, and the rest are known fixed values. In fact, this system should be solved in the context of elliptic curve cryptography. Actually, W1 and W2 are elliptic curve points. More so, they are actually first source group elements with respect to a pairing. The uppercase variables are also elliptic curve points, and the lowercase variables are actually finite field elements. As you can imagine, a solution is easy to find, and a solution exists as soon as a very simple set of constraints are met. Okay, so if you understood all of this, in fact, you have learned the core about the last challenge attack. But now we have to go a bit deeper. So still in a nutshell, the attack targets incorrect implementation of Fiat-Shamir transform of KZG-based snarks. In fact, as I said, it can be generalized, and the last challenge attack may apply to any based KZG protocol in which the Fiat-Shamir transform has been incorrectly computed with respect to the KZG-proof batching challenge. More concretely, the last Fiat-Shamir challenge U must be computed incorrectly as independent of certain components of the proof pi. And the outcome, unfortunately, is quite disastrous for the verifier, as it enables a malicious prover to compute an argument pi prime for a false statement, while the argument pi prime is accepted with very high probability by the affected snark verifier. In the rest of the talk, I will discuss briefly the setting in which the attack was found. I will review the Fiat-Shamir transform, as well as the KZG single point and multi-point evaluation scheme. I will discuss in detail the last challenge attack, and I would highlight implications and conclusions. So the attack was discovered in the following setting. It's about layer 2 ZK rollups. And in fact, what do ZK rollups do? They execute transactions off-chain. They require a snark prover, which provides an argument pi, this argument testifies that the transactions were actually executed correctly. And there exists onto layer 1 an embedded snark verifier that verifies the correctness of this proof pi. If the correctness of proof pi is hence testified, the state of layer 2 onto layer 1, as well as the state of layer 1, get updated. So now, as a quick reminder, the Fiat-Shamir transform, it's a quite useful tool. It allows us to obtain non-interactive arguments from interactive arguments. The security of the non-interactive arguments can be proven in the random oracle model. And in practice, using the Fiat-Shamir transform means that both the non-interactive prover as well as the non-interactive verifier must independently compute the same challenges as the hash of the full transcript of the communication so far. Okay, and in order to complete all the knowledge necessary to understand the attack, I will give a brief reminder of the KZG polynomial commitment scheme. I will do so for both the single point and multi-point evaluation scheme. So the KZG commitment scheme assumes two parties, the prover and the verifier. It also requires a pairing-friendly elliptic curve and hence an associated secure pairing, a scalar field, and two pairing source groups, among other things. And it consists of three algorithms, the first of which is a generation algorithm, which, using a multi-party computation, computes a secret value x that it is not shared with any of the parties, but the output is based on these secret values and is called a structured reference string, which is in fact a vector of elements from the two source groups. By the way, in the rest of the talk, I will use generator notation for the source groups. And the second algorithm is a commitment scheme, which simply takes a polynomial commitment. It outputs a first source group element. And finally, the more involved algorithm, it's actually an opening procedure. It has a larger input. It contains, the input consists of a set of commitments, one evaluation point for like single point evaluation KZG, and a corresponding list of evaluations. And it follows 3 rounds. In the first round, the verifier simply selects a uniformly random scalar from the scalar field. In the second round, the prover, using this scalar, computes batching polynomials, which are based on quotient polynomials, corresponding quotient polynomials. And the prover outputs as KZG proof simply a commitment to this batching polynomial. So this is the KZG proof for single point evaluation. In the final round, the verifier performs some further computation with respect to batching commitments, and it outputs accept if and only if a certain pairing verification passes. Okay, now let's look actually at the multi-point evaluation scheme, because this is crucial in order to understand the attack. N, in this case, will be greater or equal than 2 and will denote the number of evaluation points for the KZG scheme. The multi-point evaluation scheme we abbreviate by KZG MES. The generation algorithm and the commitment algorithm are the same as discussed previously. What differs and is more involved is actually the opening procedure. As you can see already from the inputs, we have a vector of sets of commitments. We have a set of evaluation points, and we have a vector of sets of evaluations. And already we see in the first round that the verifier has to now output n random uniform values, one value per evaluation point. The prover also has to output or compute n polynomials and batching polynomials, one batching polynomial per evaluation point and per batching random value. The KZG proof in this case consists of n commitments, each commitment to one of the batching polynomials. And we are in round 3, where we see the biggest difference. The verifier has to choose a random value u, a random scalar. This was not before on the previous description. This was not necessary. And then the rest is very similar. The KZG verifier outputs accept if and only if the corresponding pairing check passes. A quick note here that is quite important, and we'll come back to this. The last challenge u, so the last random challenge that the verifier has to compute, is actually only computed by the verifier and is never computed or used by the prover. Actually can be computed, but is never used by the prover. And first things first, when we talk about security, if this was not clear so far, we make it clear. KZG MES has completeness and knowledge soundness in the algebraic group model. And if you want to see the full details, please follow those described in Lemma 6 from our latest paper. Okay, so all of this was interactive version, and we proven security, but what happens in the non-interactive version, which is actually what is used in practice, and how do we obtain non-interactive version? First of all, the non-interactive version of the protocol you have just seen is obtained by applying the Fiat-Shamir transform, and also it can be proven that the non-interactive version is secure in the random oracle model. The first reminder is that all challenges are computed by both the non-interactive prover and the non-interactive verifier as the hash of the communication of the entire communication transcript up to that point. And the second reminder is that the last challenge u is actually only used and computed by the non-interactive verifier. All right, there are, however, further considerations that should be taken into account. In a real-world implementation, developers might be worried, and actually they are for good reason worried about efficiency. So this means they might want to reduce computational cost to the minimum, and they wonder whether including the entire transcript is actually necessary, because hashing costs are actually costs. So much so that the following dilemma might occur. Does non-interactive KZG MES still remain secure, in the sense, does it still have knowledge soundness if the non-interactive verifier, in fact a variant of it, computes the last challenge u as the hash of only a part of the full transcript that excludes, for example, some of the PyKZG components? This is what the last challenge attack is all about. In order to describe the last challenge attack, I will just introduce some very brief notation. I denote by PKZGN the malicious non-interactive prover that will work as described on the slides, and by V prime KZGN I will denote the following variation of the correct non-interactive KZG verifier. So V prime KZGN simply works as the correct verifier, with the only change that when computing the last challenge u, it hashes the full transcript, excluding the first two components of PyKZG. And now let's see all the steps of the attack. On this slide, I will describe the first 3 steps. The first step is actually a bootstrapping step, and it describes how the prover...
Can I ask a question?
Yes, please.
What is gained by removing those two components of Pi? Why is it not simply easy to include them in the last
It is simply a point of efficiency. Some developers feel that if they remove the part of the transcript from the hash, they gain in efficiency. Or if they remove further parameters from the entire transcript, simply like computing the hash will be faster, and they reduce the computational cost on the verifier.
Is it like 30% reduction in negligible?
It is small. Okay. It is small reduction, but very small reduction. But it's nevertheless something that the idea of cutting corners that is problematic here.
Okay. Thank you.
So in the first step, the malicious prover will act as follows. It will simulate a single instance, single evaluation point KZG for an arbitrary polynomial, and it will be evaluated at an arbitrary value. And using the inputs for the KZG pairing, the malicious prover will simply compute values A and B such that the following pairing check holds. Now, also in the second step, also the malicious prover will set all green font variables to their domain-respecting to some domain-respecting but yet arbitrary values. So all these green font values are actually all the inputs to the opening procedure, and as I said, the malicious prover can set them to any arbitrary values of its choice, but within their respective domains. Moreover, the malicious prover can also set to any arbitrary values within the first source group the values W3 to WN from the ZKProof. And the malicious prover does that in order to create, finally, a proof pi prime KZGN, which is a proof for a false statement. And in order to obtain this pi prime KZGN, all that he needs to do is just to compute some values W1 and W2, which pass the final verification check in the pairing. Let's see how it does that. So the attack continues. Now simply the prover in the third step deterministically computes values F1, Fn from the first source group following round 3 of KZG MES. So it simply now follows the correct logic. And in step 4, this is actually the problematic step. This is the only part when the honest verifier, actually, the correct verifier deviates, and this is the reason why the attack is possible, because V prime KZGN computes U as the hash of the full transcript, but it omits the values W1 and W2. So basically, it includes everything that was fixed before by the prover, but does not include something that can be later decided by the prover. And from this moment onwards, basically the deviating verifier is doomed. Because what can happen is that the malicious prover exploits the lack of awareness by the verifier by simply solving the following system of 2 equations with 2 unknowns. And this is déjà vu. You have seen this system of equation in the beginning. We have talked about it. So this system can be solved with high probability. And also now you see where the values A and B are used. So the values A and B, as you can see, they come in from the pairing check described below. So once the values W1 and W2 are computed, and as we said, this is possible with very high probability, the malicious prover simply fills in the corresponding slots, remaining slots of the pi prime KZG proof. And at the very end, surprise, surprise, the affected verifier accepts the pi prime KZG proof as valid with probability 1. And now let's see some possible implications in the real world. I will also, of course, describe the implication in the context in which the attack was found. So let's imagine P prime, a malicious snark prover, which has a P prime KZGN subcomponent. So basically what can happen is that P prime can set itself as the owner of all the assets by simply changing the Merkle root, which is considered as a public input, and thus this malicious snark prover can simply steal users' funds, even all users' funds. So this is, as you can imagine, if such attack happens in the wild, is quite disastrous. In conclusion, today I have presented a new type of attack, which we called last challenge attack, and this can occur if some incorrect implementation of the Fiat-Shamir transform happens with respect to KZG-based snarks. This attack exploits the fact that the last challenge in the Fiat-Shamir transform with respect to the verifier was computed incorrectly as independent from some parts of the transcript. And finally, I would like to draw your awareness that even though this is a Fiat-Shamir related attack, and this is related to weak Fiat-Shamir, this is also different. While weak Fiat-Shamir is possible because certain parts of the public input are not included in the transcript, this has different reasons. Our attack has different reasons of existence simply because other parts of the transcript are not included in the hash which derives the challenges. So as a takeaway message, when computed the Fiat-Shamir challenges, please do take into account the entire transcript. And yes, even though it's expensive, or might look a bit more expensive, we do have to follow the protocol. So yes, please do mind your Fiat-Shamirs. Thank you.
Do you have questions for Oana? It was a very clear presentation.
Thank you.
All right. Okay.
Hi, thank you for that. I'm not sure if that was actually your answer. If the answer to this question is your answer to his question, but do you have a sense of why they took these out, or like what they hoped to gain? Was it simply efficiency? And like, if so, why just these two values and not some other set?
It might be the case, that's a good question. It might be the case that they actually might have removed some other values from the transcript, but these two are actually critical for mounting the attack. So, yeah. It was in some sense good that these values were removed, that we could show the importance of actually following the protocol correctly.
Yep. You could have told me. Thanks.
So one question, why would the verifier use, because if I understand correctly, the problem here is that the verifier squeezes basically a challenge from the sponge without having fed the right things to it, right? Why would the verifier want to squeeze that challenge from the sponge as opposed to genuinely generating a random challenge, which is something that the prover cannot do in traditional Fiat-Shamir, right? But the verifier, why is there a need for them to squeeze challenges from a sponge as opposed to generating them at random? Or is this for context where random generation is not possible?
Right. I think if I understand correctly, the point is why do we need Fiat-Shamir, and why don't we use like random challenges from the verifier?
Oh, on the verifier side, correct? Yeah.
Mm-hmm. We can, like in theory, of course, we can have the interactive version, which I explained on the slides, and in which the verifier simply uses randomness, and that is proven to be knowledge sound and have completeness, as shown in detail in the paper that I highlighted. But in real life, we cannot afford to have interactivity on the blockchain. So we have to have a non-interactive version, which is also secure. The best way we know so far how to transform an interactive protocol into a non-interactive one is using the Fiat-Shamir transform, in which actually the challenges which were random before are now replaced by hashes of like the entire transcript of the communication. This is, some people would argue this is not perfect, and we know it's not perfect, but this is the best we can do to match both efficiency and security. I think
Yeah, okay, so thanks very much. I do understand why one uses a Fiat-Shamir transform to generate challenges for the prover, right? Because it is the prover that needs to produce a proof non-interactively, right? My question is, why would they also do that on the verifier side? Why would the verifier need to squeeze the challenges out of a sponge, since they don't have to send anything to the prover afterwards?
I mean, it's they have both the prover and the verifier have to agree on the same challenges. So this is like it's a non-interactive procedure. So basically, what happens on the side of the prover, the entire computation is being computed, including the challenges, and on the verifier side, these are recomputed, and the part of the verification procedure includes the same computation.
Oh, I see. So the prover also squeezed the same challenge at some point at the end. Is that what you're saying?
Wait. So tell us.
I think this is the case where you're using a KZG batch opening proof within another Stark. So it's not the case where you're trying to batch verify opening proofs independently, in which case you could have the verifier choose a random challenge. And then, in fact, Appendix B2 of the Zcash protocol spec says how to do that for Grok16. But yeah, that's not the case here.
Yeah, so if I understand correctly, the point is whether this protocol is independent of some other protocols, but I think this is also used within some recursion procedure, and yeah, probably that was the question.
Oh, answered. Okay, thank you very much.
Thank you.
For this talk.